Well, hi there, sports fans, and welcome to another exciting edition of Physics 12. And today we're going to be looking at lesson 6.3, which is on electric fields. So the electric field, it is the force on a small charge divided by the charge itself. Now that may sound a little bit confusing, but all that means is that the electric field, if you can determine the force on a particular charge, then you just divide by the charge itself, and that gives you the electric field. So here's an example of that, and if you have an electric field measured to be in that direction, if you have a positive charge, then the force on that charge will be in the same direction as the electric field. We'll talk about that a little bit more in just a minute. On a negative charge, the electric field will be in the opposite direction of the electric field. So the force on a positive charge will be the same direction as the electric field, and the force on a negative charge will be in the opposite direction of the electric field. So for a point charge then, the electric field is determined to be you just take the formula for electric force and then just take out the test charge, and that'll give you the electric field. So if you look at that a little bit more closely, the force on a point charge in an electric field is given by the formula here. So the force is the point charge in the electric field multiplied by the electric field. And also we have the same sort of thing as we talked about with electric forces. If you have more than one, then you have to superimpose the different forces and add them like vectors. It's the same sort of thing with electric fields. So if you have more than one electric field, you will just be simply adding them as vectors, just like we did with electric forces. Now, let's make some comparisons with gravitational force and gravitational field. So here's our formula for gravitational force, and there's our formula for electric force. And you can see how similar they are. And we also know that force of gravity is the mass of an object in that gravitational field times the strength of the gravitational field itself. So F equals mg, and we know that g is just simply the force of gravity divided by the second mass. So whatever mass you have within that gravitational field, you just divide it by that particular mass. And so therefore the gravitational field is just simply g times the mass that's producing the gravitational field divided by the distance squared. And so we can determine the gravitational field based upon the mass of the object that's producing the gravitational field divided by the distance from the gravitational field that you are. So let's compare that with electric field. Electric field then, or electric force, is determined by the charge within the electric field. So we also sometimes use a lowercase q instead of an uppercase q. And so the electric field then is if we just rearrange this equation like we did with this one here, the electric field is the electric force divided by the charge that's within that electric field. And so that is given by K times the charge that's producing the electric field divided by the distance squared that you're from that particular charge that's producing the electric field. So you can see the similarities that we have with gravitational force and gravitational field. There's a lot of parallels then with electric force and electric field as well. So problem solving in electrostatics, electric forces and electric fields. First of all, you draw a diagram. We've heard that before. Draw a diagram, show all the charges with their signs and electric fields and forces with directions. Then you calculate the forces using Coulomb's law, which we have talked about. And you add the forces as vectors to get your result for that particular problem. So field lines then, let's look a little bit more closely at field lines, electric field lines. The electric field, it can be represented by field lines, and these lines start on a positive charge and they end on a negative charge. So if we look at this diagram right here, here we have a positive point charge and it is producing an electric field which its direction is away from that positive charge. And so, as it says here, it starts on a positive charge and goes toward a negative charge or away from that positive charge. If you have a negative charge producing an electric field, then the direction of that will be toward that negative charge. So if we can say it a little bit differently here, which this was probably a little bit less confusing, where the electric field direction is determined by the direction of force that the electric field produces on a positive test charge. So in other words, if you have an electric field, put a positive test charge anywhere in there, and the direction of force on that positive test charge will tell you the direction of the electric field. So obviously then, if you put a positive charge near this positive charge, so we have a positive test charge, obviously the direction is going to be away from that positive charge. If we have a negative charge and we put a positive charge anywhere, a positive test charge anywhere near that, then the direction of force on that on that positive test charge will be toward that negative charge that's producing the electric field. So it all sounds a little bit confusing, but just think of it as just put a positive test charge, and whatever direction the force is from the point charge, that'll be your direction of electric field. So the number of field lines then starting on a positive charge is proportional to the magnitude of the charge. So as the field lines get closer together, the field is stronger. And similarly, the number of field lines ending on a negative charge is also proportional to the magnitude of the charge. So again, field lines, if they're closer together, stronger electric field. If they're further apart, a weaker electric field. So the electric field is stronger where the field lines are closer together. And now if you look at the example of a dipole, if you have two equal charges but they're opposite in sign, then your field lines will look something like this. And once again, it's just simply you put a test charge, a positive test charge anywhere within that electric field, and the direction of electric field will be determined by the direction of force on that positive test charge. So it'll be from the positive pole toward the negative pole. So if we summarize the field lines then, field lines, they indicate the direction of the field, and the field then would be tangent to the line, it'll be a tangent to the field line. And the magnitude of the field is proportional to the density of the lines. And lastly, field lines, they start on positive charges and they end on negative charges. So the number then is proportional to the magnitude of the charge. So once again, just within electric fields, to determine the direction, you just simply put a positive test charge anywhere in there, and the force on that positive charge, the direction of that force will tell you the direction of your electric field.